In this video, we're continuing on the series of the board bring up for the set-bred PCB that I designed, featuring a Xilinx Zynq system on chip, essentially half application processor, so a dual-core processor that can run Linux, and half FPGA, so to speak. Quite excitedly, in this video, we'll be bringing up PetaLinux, which is Xilinx's version of embedded Linux, and I'll show you how to run this on this custom system and get this up and running. There's not too much information on how to do this for custom hardware online, so I thought I'd contribute to that a tiny bit. Before we continue, make sure to check out the previous series of videos, and I have an FPGA playlist on my channel. We're already 4 or 5 videos in, so I went through the whole board bring up, looking at the DDR memory, non-volatile memory, Ethernet, and so on. So make sure to check out those videos so you're up to date, because I will be assuming some prior knowledge based on these videos. As a quick summary, what we checked out in the first few videos were just even programming this device, so via the JTAG and USB to UART connections through this FTDI chip. Then we looked at bringing up the DDR3 memory, because this needs to be done for us to run any application on this device, because the on-chip memory on the Zynq is rather small. We also checked out how to interface and flash the QSBI memory, and then we checked out the gigabit Ethernet connection, did a bandwidth test, and saw that we can indeed reach pretty much the 1 gigabit throughput. In this video, as I said, we will be bringing up PetaLinux on the system, so for me, rather exciting as well, bringing up an embedded Linux system, very basically, just the minimum amount that we can run embedded Linux on this board. Running an embedded Linux then will allow us to check the eMMC memory, where we have 4 gigabytes of this, as well as the USB high-speed physical layer connection, which enables USB on the go, but that's probably reserved for a future video, as the PetaLinux build-up is rather lengthy. Thank you very much to PCBWay for sponsoring this video. This set-bred PCB I had manufactured and assembled by PCBWay in China, and they did a great job for this fairly complex design, 10 layers, 0.1mm track spacing and track widths, small via holes and so on, with custom stack-ups and impedance control. For this, I used their advanced PCB service, and I had 3 of these prototype boards made, and as you can see, there are many different options here, up to 60 layers, anything you could possibly want for your custom PCB, including HDI PCBs and so forth. I will be making a hardware design walkthrough video in the future once we've gone through the board bring up, so stay tuned for that. Thank you also very much to Altium for sponsoring this video. I designed this board completely using Altium Designer, using many of the cool Altium 365 features such as version control, and I also used many of the Altium Designer tools for high speed such as delay tuning, impedance control calculations, which I needed for this design. If you'd like to give Altium Designer a try for yourself, please check out the link in the description below, or go to altium.com/yt/philslab, and you can get yourself an Altium Designer free trial and 25% off your first license purchase. As I said before, we will be looking at how to run PetaLinux on our custom system, how to configure PetaLinux, how to build it, install other tools, and so on. This is a fairly involved process, and I won't be going much into detail, but I'll be showing you enough for you to be able to do this on your own system. A lot of the online tutorials assume some sort of pre-made board, and they'll give you some board support package and just say do this, and I hope to help that a tiny bit by seeing how you can do this for a completely custom system. Due to time constraints, I won't be telling you too much about embedded Linux, what PetaLinux is, and so on. Very basically, it's an embedded Linux distribution maintained by Xilinx with support for their devices, so this will run natively on Zynq with the right configuration. I'd strongly suggest reading through the PetaLinux documentation. There are also bring-up guides and so on, just to get familiar with this if you aren't familiar with it before. I typically use Windows for my main operating system, but for all the PetaLinux installs and flashing and so on, you will need to use a Linux distribution. This can either be directly installed on your PC, or as I have done, I'm running this on Windows in a virtual machine, and I quite like VirtualBox. So if you'd like to follow along, download VirtualBox. I will be using the latest version of Ubuntu, which at the time of making this video is Ubuntu 22.04.2. Now the PetaLinux tools, once you run them, will actually tell you this version isn't supported yet, but I haven't had issues with using this version. But that's something to keep in mind. If you'd like to follow along, make sure to install VirtualBox and also download an image of the latest Ubuntu desktop version, and then let's get started. We're now looking at my virtual machine, so this is VirtualBox running the latest version of Ubuntu. Again, I'd strongly suggest you looking through the PetaLinux docs before you continue, but I'll guide you through the process now. For PetaLinux tools to be able to run and install properly and us to be able to configure PetaLinux correctly, we need to install various dependencies. So you can either install them manually or follow this guideline 73296. That's how to install the required packages for the PetaLinux build host. If you scroll down, you'll see this file attached, which is this script, which will install all of the dependencies for you. My first step would be to download this file, right-click on the download properties, permissions, and allow executing file as program, and then you can simply double-click on this, or of course just run it in the terminal. The PetaLinux tools also require this change, so to reconfigure that the shell points to bin bash, and the way you can do that is simply run this command in the Ubuntu terminal, so make sure you do this before you run the PetaLinux tools. In any case, once you're finished with those prerequisites, you need to go to the PetaLinux tools website, and I'll leave a link to this in the description below, and click on download and licensing. Then on the right hand side, click on download PetaLinux, and this is where the main tools are located. The number one item you need is this PetaLinux installer, so make sure to download that. But there are many other packages here, for example, board support packages for pre-made modules such as the Xilinx modules and so on. However, we'll be just using the default PetaLinux tools installer, so a completely vanilla version, so to speak. Once you have that in place and downloaded, make sure to run this and install it to a certain directory. For me, I just installed it under downloads and PetaLinux-tools. Once you have this installed, we can right-click in the install folder, open terminal, and for us to be able to call the tools natively in a terminal, what we need to do is type in source settings.sh, and this will make sure that our system knows that it needs to point to these various tools and where they're located. The next thing before we can configure and build PetaLinux is that we need some sort of hardware constraints or hardware definition file. If you remember back in Vivado and from the previous few videos, we created this block design using this very simple Zynq processing system block. We set up UART1, which is our debug or terminal port, which goes to the USB to UART FTDI converter. We set up Ethernet, the QSPI flash, and so on. Or I've also enabled USB for USB on the go, as well as SD, which is for the eMMC memory. Jumping over to Altium Designer, looking at the hardware design just to familiarize ourselves, we have this eMMC memory, which is very similar to a fixed SD card, so to speak, uses a very similar or same interface, and this is 4 GB of non-volatile memory connected up to the Zynq with an SDIO connection. On the right-hand side, we have this USB physical layer, which uses ULPI to interface with the Zynq, and on the right-hand side, then we just have a USB differential pair, so to speak. I've enabled those in Vivado as before. All I had to do was enable the various buses, so SD and USB. And we'll be using those in this and future videos to verify the eMMC memory, as well as the USB on-the-go system as well, which will be the last parts we need to verify on this system. In any case, once you set up your Zynq processing system as before in Vivado, you should generate the bitstream, which includes running synthesis, implementation, and so on. And then as usual, go to the top left file, export, and export hardware to generate your XSA file. Then back in the virtual machine, you can see I've already moved over my XSA file that I exported from Vivado right here. I didn't have to open VTIS like in the last few examples. This XSA file, this hardware definition file, will be used by the PetaLinux tools to configure PetaLinux and tell PetaLinux what devices are available to it. So essentially, this will aid us and generate a device tree, a Linux device tree automatically for us based on this hardware definition file. So it'll enable UART on the port we selected, which is UART1 with a baud rate of 115200. It'll enable the DDR memory, QSPI, Ethernet interface, USB, and so on. So it's very important that you generate this XSA file based on your hardware, the same workflow as we've seen in the previous videos. Once you have that, we're now ready to start and create a new PetaLinux project. You can see this setbret peta folder here is a PetaLinux distribution I already created for a test, but will go completely from scratch. Wherever you downloaded the PetaLinux tools, right-click and open New Terminal if you are using Ubuntu. What we now want to do is run our first PetaLinux command. The first command we want to run is to create a PetaLinux or blank PetaLinux project. The way you do that in the terminal is type PetaLinux-create, and then we need to add some flags. With any PetaLinux command, we can add --help, press enter, and this will tell us what kind of flags we can add to the relevant commands. And this will give us a good indication of what we need to be typing in. What we need to be typing in is PetaLinux-create, then we need to create a type project. We want to create it from a template. So a template could, for example, be Microblaze for a soft processor on an FPGA, but we're running a Zynq chip, so we'll choose the template Zynq. Then we need to give the project a name. So we'll do --name and we'll give it some sort of sensible name. Maybe it's setbred PetaLinux demo and then press enter. You'll see it'll tell you it's created a new project and where it's created this project in. If we go back to the directory, we can see there's a new folder created. If we go into this, it's fairly empty, just project spec, nothing too much in this. Now let's navigate to that new created folder. And now we need to include the hardware description file. If we remember back, if we go one up, this is where I stored my hardware description file. The location is pretty much irrelevant as long as you can find it and point to it. For me, it's in Home, Philip, Downloads, PetaLinux Tools. Back in the terminal then, the way we can tell PetaLinux before we configure and build this project, what we need to do is type in PetaLinux-config -get-hardware-description equals, and then we need to type in the path where our file is located. For me, that's the path we just saw, and then click enter. You can see now it's starting to generate some more information for this project, and then it'll boot into this configuration screen, which is the first configuration screen we need to check out. It pays off to go through this configuration, just see what's available. For this very basic project, we won't be needing to be changing anything, or not very much, so to speak, but it pays off just to check to make sure the hardware has been configured properly based on our XSA file. We can go to the subsystem auto hardware settings. We can see that the system processor is identified, of course, as the Zynq. Memory settings, we can see that we're using the DDR memory. Serial settings, we can see it's automatically from our XSA file identified that we're using UART1 and that we're using that at a baud rate of 115/200, exactly as we specified in Vivado. Ethernet we're using as well, Ethernet 0. We have QSBI memory attached, and we also have the SD eMMC memory, for example. What I would like to turn off, however, we can leave the rest as standard. If we go down to image packaging configuration, by default, it'll try to copy the final images to TFTP boot, and for us and for this example project, we won't be using this, and it might throw some warning messages or error messages if we leave this on. So navigate to this point and then press N on your keyboard, and that'll delete that. Then exit again, and then we can save this configuration. As you saw, we left pretty much everything as standard. This might take some time to configure, and once it's done, we shouldn't get any errors or warnings. Now that we included our XSA or hardware description file into our project settings, what we need to do next is configure the kernel. Again, we call the PetaLinux-config command, this time with a flag -c and then space kernel and press enter. This might take a little while again, so just give this a couple of minutes and don't worry if it takes a bit longer, but it'll show a very similar window to the one we just saw before. Finally, just under about 10 minutes, the kernel config window has opened. As before, there are many options when configuring a Linux kernel. Again, it pays off just to quickly browse through. For us, we won't really be changing anything, but it's definitely interesting to see what's available, what we can enable, disable. Of course, adding more features into the kernel will take longer to build and will create a larger image that needs to be able to fit on the Zynq or whatever memory you put this on. As a default setup, we don't actually have to change anything. Luckily, the PetaLinux distribution, in addition with our hardware configuration, our XSA file, has configured everything to give us a very minimal and basic PetaLinux distribution and setup. So all you have to do is go to the right arrow button and click exit. There are two additional config commands we can now run. One is uboot and one is rootfs. So let's start with uboot. Again, we use our familiar command PetaLinux-config with a flag -c and then u-boot. Again, this might take a bit of time before the menu appears again. Again, another 5 to 10 minutes have passed and we get a similar configuration window as before. Again, please make sure to go through this, just have a brief check of what options there are, but for us, we can leave most of this as standard. If you want to enable different boot modes and boot options, for example, you could go to boot options, boot media, and enable support for QSBI flash by hovering over and pressing Y, or SD cards and eMMC memory as well. So let me just select those, exit, and again, there's many different options we have here as well. Let's just leave these as standard and select exit, then press yes to save. We're almost ready to build this project, but I'd like to also show you the final configuration command, again, typing in PetaLinux-config with a flag -c and this time rootfs, so root file system, and press enter. This will pop up pretty much straight away, and here you can configure the rootfs root file system as you please, depending on your needs, of course. For example, we can add in file system packages, programs, applications, and so on. Again, this will increase the size of the image, will take longer to build, and will be a larger image, of course, so you need more memory. And through this rootfs configuration, you could also add in your own applications, for example. So for example, if you go to user packages, there are some demo projects here. We can add in the GPIO or peak poke demos by selecting and going and pressing Y on the keyboard, exit, and then we save by pressing enter on yes. Now we're pretty much ready to build this project. All we have to do is type in the command PetaLinux-build and press enter. Now this can take quite some time to build, especially if you've started a completely fresh build. Once you've built this once and make small changes to the configurations and then run the PetaLinux build command again, the time is significantly shorter. For a fresh build with these almost default options selected, this takes about 20 to 30 minutes on my system. So let me pause the video and I'll see you once this is done. So after about 15 to 20 minutes, the build should have completed with no error messages. Before we connect up our FPGA board, our ZBread board, to the computer, what we need to do on our Linux distribution is install the cable drivers. And unfortunately, this means we also have to install Vivado. To install the cable drivers, so the drivers we need to flash our FPGA, our Zynq system on chip, we have to navigate to wherever you installed Vivado on your Linux distribution. For me, that was on the computer, Tools, Xilinx. Then in Vivado, go to your version number, then on Data, scroll down to XICOM, cable drivers, whatever Linux version you're using, so 64-bit Linux for me, install script, install drivers, and then we need to run install_drivers this script before we plug in our ZBread board. Make sure to do that before we proceed with the next step. I've connected my ZBread up as usual. I have my DC barrel jack for power. Underneath that, I have a micro USB cable, which plugs into my host computer, connects to the FTDI USB to UART, as well as USB to JTAG converter, which then hooks up to the Zynq, so we can program it and we can also open the console. As you can see, I've also attached an Ethernet cable to the RJ45 connector, and that's hooked up to my router of my home network. So let's move back to the computer now. With the hardware connected as just shown, make sure if you're running a virtual machine to forward your USB devices in your system. Of course, if you're just running this as a straightforward host machine without any virtual machine, then you don't need to do this. Let's just check that our USB devices show up. So the USB to UART and USB to JTAG, where we can do that in Ubuntu is ls dev tty USB asterisk, and we can see USB 0 and USB 1. USB 0 happens to be the USB to JTAG converter, so for programming and debugging, and USB 1 is our USB to UART converter. Whichever program you'd like to use to monitor the console, feel free to use that. I'm going to be using Putty, so I'll just start it like so. We want to select serial, then we want to select TTY USB 1, and remember our baud rate is set up to be 115200, and let's just open that. Then again, in my ZBread PetaLinux demo folder for our PetaLinux project, right-click and open in terminal. Now we're ready to flash the Zynq via JTAG and upload our PetaLinux images to the device. Now this will take quite some time and with no real progress bars. In some cases this can take even longer than the build itself. In future videos I'll show you how to actually flash this, for example, to eMMC or QSPI memory to be able to boot from that. But for now the simplest way of testing this is flashing via JTAG and booting via JTAG. The command we have to enter is PetaLinux-boot -JTAG -kernel. Then press enter. You'll see a few messages, but then you'll see that the FPGA is being configured, and now I can see that the done LED has turned on, and now it'll start to upload the .elf file, and after that it'll upload the Linux image. And again, this will take quite some time, so I'll pause the video and come back once we're ready to boot. Now we can see on the left-hand side, initially U-boot will start. We'll see that the Zynq CPU was detected, various memories were detected, for example, the DDR, Ethernet, and so on. You can ignore most of this for now, and we'll see more once the actual PetaLinux image will start to boot. From this point on, it's quite disconcerting because we don't see any activity either on the console or on the right-hand side for quite a large amount of time. So make sure to just stick with it, don't touch it until it's booted PetaLinux. Now we can see Linux is actually booting up, so this took about 20 or 15 to 20 minutes to start up. And we'll go through all these messages just to check what's been set up and how Linux is booting into this. And finally now we're at the login prompt right at the bottom, so this is pretty cool. We've booted up PetaLinux and now we just have to log in. So let's just scroll back up at all of these messages. After U-boot, then launching into PetaLinux, we can see we've discovered the Gigabit Ethernet, or GEM for short. We can see it's starting to boot from JTAG. Then we're starting the kernel, starting on the first core of our CPU, and this is actually a dual core CPU, which it'll detect in just a second. We can see how much memory we have available. Apologies for the rather small font. It's detected a dual core CPU, so CPU 0 and CPU 1. Then we can see it started the Ethernet interface and the networking interface, and you can go through all of these messages in detail just to see what drivers, for example, it's loaded as well. What we can also see is the eMMC memory it's detected, this eMMC block 0. It's detected about 4 gigabytes of memory, which is already a great sign as well. We have our login prompt, and for this version of PetaLinux, so from 2022.2, the login is no longer root. What we have to do is type in PetaLinux as the login, and then we'll be prompted to change the password. So I'll just change the password to ABCD, because this is just a test system, and now we're in PetaLinux. And we can run our usual Linux commands, for example, listing directories, changing directories, and so on. Of course, this is a very, very minimal setup and distribution, as we've done a very basic config, remember, when we built and configured PetaLinux. So there's not too much we can actually configure here or look at, but this video was just to show you how you can create your own PetaLinux build specific to your target application. What I will show you just as a quick test, of course, is that the Ethernet link hopefully is working. We can see that the link actually here is up at 1 gigabit per second. So for example, because it's connected through my home network to the internet, I can ping Google, and we can see we get pings back and a certain response time. If I run ifconfig, I can also see the Zynq's allocated IP address. So in my home network, that's 192.168.178.44. So if I open a terminal on my host machine, for example, I can ping 192.168.178.44. And you can see, of course, I'm getting a fairly fast response time because it's just on my home network. So this all works as well. Looks like the Ethernet link is up. What we can also look at is the eMMC memory, see if we can create some partitions just to verify that quite quickly. I'm using this particular eMMC 4 gigabyte memory. What we can do, I'll list the devices with this command, and we can see we have eMMC block 0, and everything with eMMC block is our eMMC memory. If we want then, for example, create a partition, we'd have to call fdisk with sudo, pointing towards eMMC block 0. We have to enter the password, of course. We can print the partition table with P, for example. And you can see, this is from my previous test, I already had created a partition of size 128 megabytes. But of course I could delete that partition by pressing D, and then I can press P again to list my partition tables. Then if I want to create a partition, I can press N for new. I want a primary partition, partition number 1. First sector I'll start at 16, and I'll generate. So type in +512M, and then we can press P again. And then we can see we've created a 512 megabyte size partition, just an example. And then we also need to type in W to write the table to the disk to make sure this partition is actually created and saved. I know this is a very simple example just to check that Ethernet, the eMMC at least, is showing up when we can create partitions, and that's already a very, very good sign. We also, of course, added the Peek Poke app in, and just to show you that this works as well. Peek lets you look at a particular memory address, so I'll type in sudo peek. We can look, for example, at different memory addresses, and these programs are then automatically stored in user bin, and we can see we have Peek and we have Poke here as well, just as an example. In summary, this video hopefully showed how to create your own PetaLinux build for a completely custom system, just configuring the very basics just to check if we can even run PetaLinux on a system, and that way we can again verify the DDR memory, the whole JTAG chain, as well as we looked at briefly the eMMC memory, and again just look into the gigabit Ethernet link, seeing this is a lot simpler to set up once we have Linux actually running on our system. In future videos, I would then like to go into more detail on the eMMC memory, just verifying that, maybe doing some speed tests, how we could maybe boot from the QSPI or eMMC memory. As you saw, the JTAG boot is rather slow indeed. And then, of course, lastly, we need to also verify the USB physical layer for this USB 2.0 high-speed link for USB on the go. And that will then conclude pretty much the board bring-up series for this particular ZBread PCB. Thank you very much for watching this video. I hope it was helpful, and I hope it showed you how to use the PetaLinux tools to build a custom configuration for your custom hardware. If you liked the video, please do leave a like, a comment if you have any questions, and don't forget to subscribe so you don't miss out on future videos. Thanks again for watching, and I hope to see you in the next video. Bye-bye.